Welcome back everyone. In this lecture I will prove that S lambdas that we constructed which is the span of tabloids, so that will be indeed irreducible representations. So, for that we need this following technical proportion. So, which I recall again. So, you take this lambda mu being two partitions of n and fix T lambda S mu, they are tableaus such that this A T lambda applied on S mu is non-zero. So, then we can conclude that lambda must dominate mu, and not only that, whenever lambda equal to mu, when you apply this A T lambda on S lambda, you always get up to sin E T lambda. So, this is a very important proposition, and this will be proved playing around with this with the symmetric group. Okay, so of course, we use the dominance lemma. First, we want to understand how to apply this A T lambda on S mu. So, recall that the definition of A T lambda. So, more or less this proportion is what gives the purpose of the definition of A T, because the A T is defined to be the sign alternating sign operators. Okay. So, you can see that this operator is going to kill certain tableaus and then it will leave certain tableaus non-zero, and those can be obtained by with the information about elements being in the same row of S mu or not. So, let us make these things very clear. So, assume that so this is the case 1 where we have two elements, let us say I j, that are in the same row of S mu and the same column of T lambda. Okay. So, let us say two elements I and j that are in the same row of S mu and are also in the same column of T lambda. Okay. So, these entries I j, when you are looking at S mu, so they lie somewhere here and they lie somewhere here, and when you are looking at T lambda, so I am looking at columns, they lie somewhere here and then somewhere here. Okay. So, now what one can do, one can look at this transposition I j and we can apply that on S mu. So, if you take this tableau S mu, look at this tabloid corresponding to the tableau S mu. So, then you apply this transposition I j and then look at it. So, then what this transposition will do, this transposition will interchange this I and j, but up to this equivalence relations of tabloids, we can see that it will not change the equivalence relation. So, that means we get again S mu. So, this means this is same as the identity element applied on this S mu, because I j applying on S mu same as identity applying S mu. So, that means whenever I take this operator phi mu and then apply this identity minus phi mu, apply this I j, and this operator on S mu is going to kill this S mu, because identity is not going to change anything. I j is also up to this equivalence of tabloid, it is not changing anything. So, because they fixes, so this difference is going to kill. So, now what we can do, we can take this H to be the subgroup generated by this transposition I j, which is a subgroup of Sn. So, now since we have fixed this tabloid T lambda and this ij lies in the same column. So, one can realize this subgroup as subgroup of the column stabilizer of T lambda. So, what we will do, we just realize this as subgroup of column stabilizer. Recall that this is the column stabilizer of T lambda. So, here we realize this H as a subgroup. So, now what we can do, we can look at the set of left coset representatives of the H inside this C T lambda. So, we can label them as, let us say sigma 1 etcetera sigma k. So, this is the set of left coset representatives of C T lambda H coset representatives of H inside C T lambda. So, now once we fix this, so then we can do the following computation. We take this A T lambda and then apply it on S mu. So, then by definition this is going to be summation pi comes from the C T lambda sine of pi, and then you apply this phi mu of pi on this S mu. So, by definition you can see that this is exactly equal to summation pi comes from C T lambda sine of pi, and then we just apply pi S mu on this. So, now note that we can actually replace this pi. So, you can rewrite this C T lambda as disjoint union of sigma R H, where R range from 1 to k. Now, note that H is nothing but identity and this transposition ij. So, now using this, if we rewrite this sum, we can see that this is exactly A T lambda applied on S mu is going to be summation R range from 1 to k, the sine of sigma R phi mu applied on sigma R plus sine of sigma R and then this transposition ij times phi mu applied on sigma R ij, and then this entire thing you apply it on this class S mu. Okay. So, now it is clear that the sine of this is going to be minus of sine of sigma R, and this ij is going to fix this S mu. Okay. So, that means I can rewrite this as R range from 1 to k sine of sigma R times phi mu applied on sigma R times phi mu identity minus phi mu ij, and then you apply it on this S mu. And note that we just realize this term is exactly 0. So, that implies that this is exactly 0. So, this tells us that whenever we have two elements ij that are in the same row of S mu and as well as in the same column of T lambda, then this A T lambda S mu must be 0. So, that tells us that from the hypothesis, so this should never happen. So, if we go back to the hypothesis, we can see that we have this A T lambda applied on S mu is indeed non-zero. So, that means what we get. So, case 2 that A T lambda S mu is non-zero, which would imply immediately that T lambda S mu they satisfy the hypothesis of the technical dominance lemma that we proved. So, that means the elements of each row of S mu are in different columns of T lambda. So, now using the dominance lemma, this would imply that lambda indeed dominate mu. Okay. This is just a simple application of dominance lemma. So, now what happens when lambda equal to mu? So, let us look at this. When lambda equal to mu, then we have this u lambda. So, that actually constructed using the technical lemma. So, let me just show you. So, we constructed this u lambda satisfying that the jth columns of T lambda and u lambda, they contain same set of elements for each j, and the entries of the first I rows of S mu belong to the first I rows of u lambda. So, this is how we actually constructed this u lambda. So, now if we use this u lambda that we constructed earlier, since lambda T lambda and S mu satisfy this hypothesis that the elements of each row of S mu are in different columns of T lambda. So, using that we construct this u lambda. So, now the fact that the columns of T lambda and u lambda, they have the same elements implies that there is a unique permutation sigma such that u lambda is same as sigma T lambda. Okay. So, since columns of u lambda and columns of actually each column let us say column I, the jth column entries of jth column of u lambda is same as entries of jth column of T lambda, and this is true for each j between 1 to the length of lambda. So, this will imply that we can take it as exercise that there exists sigma, which is the permutation of S n, such that this sigma maps T lambda to u lambda. Okay. And one can choose this sigma so that it belongs to this column stabilizer of T lambda. So, we do not need to choose it randomly because we are only concerned with the columns. So, one can choose it in the column stabilizer of this T lambda. On the other hand, for all I, the first I rows of S mu belong to the first I rows of u lambda, and since lambda equal to mu, so that would imply that the tabloid associated to u lambda must be same as the tabloid associated to S mu. So, okay, so let us write everything. So, the first observation is there exists sigma in C T lambda such that u lambda is given by sigma T lambda. So, this comes from the first fact. The second fact is that the first I rows of S mu, the first I rows of S mu and So, we have okay. So, in this case we assume that lambda equal to mu. So, that means the first I rows of S mu should belong to the first I rows of u lambda, but since lambda equal to mu. So, this should say that this is same as the first I rows of u lambda. So, now by induction, okay, use induction and then prove that the tabloid u lambda should be same as the tabloid S mu, okay, where mu equal to lambda, that is important thing. Okay, so this is just some simple induction that will tell you that since the first I rows of S mu same as the first I rows of u lambda for all I from 1 to length of lambda. So, this is should imply that the tabloids are same. So, now using these two observations, so let us compute what happens to this A t lambda S mu. So, note that this is exactly equal to, again we have this assumption that lambda equal to mu. Okay. So, this is exactly equal to summation pi in C t lambda sine of pi, and then we have pi S mu. So, now let us actually use the fact that u lambda is exactly equal to sigma t lambda. Okay, so, we want to just simply rewrite things, and we see that the tabloid u lambda is same as the tabloid S mu. So, that means this is exactly equal to the tabloid sigma t lambda. So, now if we substitute there, we can see that this is exactly equal to, so this you can replace by pi sigma t lambda. Okay. So, if we multiply by sigma and sigma inverse, you can actually take the this you can replace by sine of pi sigma sigma inverse. So, then this becomes exactly equal to sine of sigma inverse sine of pi sigma and then pi sigma t lambda, where pi is running over C t lambda. So, now this is exactly equal to sine of sigma inverse times summation sine of tau and then tau t lambda, where tau comes from this C t lambda. So, which is exactly equal to sine of sigma inverse, whatever that sigma we do not care, times E t lambda. So, this sign is actually just plus or minus. So, this is up to a sign, it is multiple of E t lambda. So, that is what we get in this case. Okay. So, now let us make this another lemma, which actually immediate corollary of what we have observed before. So, if we take T to be a lambda tableau and then look at the operator A t, which is defined from let us say m lambda to m lambda, and then we want to look at the image of this operator. The image of this operator, it is going to lie inside this one dimensional space, which is exactly equal to E t. So, note that by definition E t is nothing but A t applied on t. So, that means image contains E t. So, now if we take any other element, for example, some S coming from this lambda tabloid, then we know that either A t S is going to be 0 or non-zero. In 0 case we do not care, and when it is non-zero, then using the earlier lemma we see that this A t S is nothing but plus or minus of A t. So, that completes that the image of A t is nothing but this one dimensional space E t. So, we have the inner product on m lambda. Now, we are going to use that inner product. So, recall m lambda is nothing but C span of T lambda, and it comes equipped with an inner product which is Sn invariant, for which this T lambda is on orthonormal basis. So, moreover, the representation phi lambda is unitary with respect to this product. So, that we fix. So, this phi lambda is unitary. So, that is because we can actually always take Sn invariant inner product on this space, that is not a problem. So, now we fix this inner product, okay, that we call it bracket. So, this is the inner product that we are fixing. So, we are fixing the inner product so that this becomes unitary and this T lambda consisting of orthonormal basis. So, which we actually did it many times. So, now look at this operator AT and then its conjugate, then it is clear that the conjugate of this is going to be the sign of pi, p lambda of pi star for all pi comes from this CT. Now, since phi lambda is unitary, phi lambda pi are all unitary operators, that means phi lambda pi star is phi lambda pi. So, this is going to give us exactly the sign of pi, phi lambda of pi, pi comes from CT. So, that means this is exactly equal to AT. So, that means AT star is same as AT, that AT is indeed unitary operator. So, it is self adjoint indeed. So, AT is self adjoint. Okay, so now let us prove this subrepresentation theorem, which is very crucial theorem in order to conclude S lambdas are irreducible. So, we call this as subrepresentation theorem. So, what it says? It says something about invariant subspaces of m lambda. So, we fix this lambda partition and take V to be Sn invariant subspace of m lambda. So, then we have only two choices, either this V contains this S lambda or this V is contained inside this S lambda perp. So, if you assume that m lambda is direct sum of S lambda and its orthogonal complement, which is direct sum of S mu, you can see that any invariant subspace either fully contained in one part or the another part. Sorry, if S lambda is not contained in V, then we can conclude that V is fully contained in orthogonal complement of S lambda. Okay, so let us try to prove this. So, this is a very important result. So, once we have this, it is immediate that as a corollary we can see that S lambdas are irreducible. So, let us conclude the corollary first. As a corollary we can see that S lambda is irreducible Sn representation. So, how do we prove? Fix this lambda partition. Okay. So, then if I start with V, which is let us say proper subspace of S lambda. So, now it is also subspace of m lambda. So, this is also contained in m lambda. So, that would imply that S lambda is not contained in V. So, using our earlier result, you can see that V must be contained in S lambda perp. So, that would imply that V is contained in S lambda intersection S lambda perp, but since we are working with the inner product space, this intersection must be trivial, that would imply that V is trivial. Okay. So, this proves that any proper subspace of invariant subspace. So, this is Sn invariant subspace. So, that is supposed to be trivial. Okay. So, subspace theorem immediately implies that S lambdas are all irreducible. So, now let us prove this subspace theorem. Suppose first that there is a lambda tableau T and a vector V such that ATV is non-zero. So, then we see what happens. So, here is the proof of subspace theorem. So, we take T to be lambda tableau and then V to be a vector V. So, this V is Sn invariant subspace, Sn invariant subspace. So, now if V contains S lambda, then there is actually nothing to prove. So, we just assume that S lambda is not contained in V. Okay. So, maybe we can directly prove like either one of the things will happen. So, let us say like we have this situation T lambda tableau and V is element of V such that this ATV is indeed non-zero. So, now using this Sn invariance of V, we can see that this ATV is indeed in the intersection of this image of AT and V, but we already know that image of AT is nothing but the one dimensional space ET. So, this is exactly one dimensional space ET intersection V. So, it follows that from this that ET should be the CET should be subspace of V, because we assumed this ATV is non-zero. So, that since this is at most one dimensional and that would imply that this one dimensional space ET should be contained in V. So, now from this we can see that any sigma applied on ET which is E sigma t, so that should be there inside your V. So, that would imply that all tabloids, so this these polytabloids, all of them will be elements of V. All polytabloids, they are all contained in this V. So, that tells that this entire S lambda should be contained in V. Okay. So, this actually proves the case 1. So, the case 1 we assume that there is T lambda tableau and V in V such that ATV is non-zero. So, now the case 2 is going to be the contrapositive of that. That means for all tableau T in lambda tableau and for all V non-zero element in V, we have that ATV is 0. Now, note that the inner product V E T is going to be exactly equal to the inner product V by definition of AT E T, AT applied on T, but AT is self-adjoint. So, in particularly this is going to be exactly equal to AT star V T, which is exactly equal to ATV comma T. Now, since ATV is 0, so this is going to be 0. So, this implies that V is orthogonal to CET for all T. So, that implies that V is orthogonal to S lambda, that means V is in S lambda per. So, this proves either invariant subspace contains S lambda or it is contained in the orthogonal complement of S lambda, and that proves that S lambda is indeed irreducible. Okay. So, this indeed completes the proof of irreducibility. So, now we need to show that given any two partitions that this S lambda and S mu, they are indeed non-isomorphic. So, for that we need to understand the multiplicity of each S mu inside M lambda. So, for that we need to first understand what happens to the home space of phi lambda and phi mu. So, let us try to understand that. So, here is the lemma. So, like I said, we want to understand this home Sn, let us say m lambda m mu, in order to understand Hom Sn S lambda m mu. Okay, so these are all the spaces that we are interested in and we want to understand what they are. Okay, so that is why we need these following lemmas. So the first lemma says, suppose that lambda mu, let us say partition of n, and let T being an element inside this Hom Sn phi lambda phi mu. If S lambda is not contained in the kernel T, so then we can conclude that this lambda dominates mu. So moreover, if we assume that lambda equal to mu, so then we can conclude that T restricted to S lambda is nothing but scalar times identity. So which is some scalar times identity map on S lambda. And this again follows immediately from subrepresentation theorem. So since the kernel T is indeed Sn invariant, so you can see that kernel T is Sn invariant. So now since it is Sn invariant and given hypothesis that S lambda is not contained in kernel T, so that would imply that S lambda not contained in kernel T would imply that S lambda perp indeed contains kernel T. So this is something we conclude using the subrepresentation theorem. So now once we have this, then for any tableau, lambda tableau T, it follows that T E T is indeed non-zero, because so T E T is going to be like, since E T is coming from S lambda, T E T is again going to be in S lambda. So T E T must be non-zero. So then this is nothing but T A T applied on T, but note that A T is alternating some of these operators coming from Sn. So, and since T commutes with the Sn action, so T and A T will commute. So this is going to be exactly A T T T. So now T bracket T is a linear combination of mu tabloids, and so there exists mu tabloid bracket S such that A T bracket S must be non-zero. So since this T bracket T is a linear combination of mu tabloids, so that is just by definition. So that means there exists tabloid S which is mu tabloid such that A T applied on S must be non-zero. Otherwise, this A T T bracket T will become 0. So that we do not want. Now since A T bracket S is non-zero, that would imply immediately that this mu is dominated by lambda, because this is mu tabloid and this is lambda tabloid, and we just proved that whenever A T bracket S is non-zero, that would imply that lambda dominates mu. So that proves the first part of the lemma. For the second part, assume that lambda equal to mu. If we take lambda equal to mu, then T E T is going to be again A T T bracket T, because T commutes with A T, and note that AT of anything, okay, this is just some linear combination of mu tabloids, and AT applied on any mu tabloid is up to a sign multiple of ET. So, that means this is going to be element of CET, and which is a subspace of S lambda. So, that means T S lambda, okay, we already know that T S lambda contained in S lambda because T is Sn invariant. So, now note that S lambda is irreducible and T maps S lambda to S lambda, and it is also Sn invariant. So, that would imply that T must be some scalar multiple of identity. So, that follows from Schur's lemma. Okay, so, this conclude that the T restricted to S lambda must be a scalar multiple of the identity map. So, now let us use this and then conclude something about the multiplicity of S lambda inside our M mu. So, we are interested in computing the multiplicity of S lambda inside M mu. So, which is by definition we know that which counts exactly the dimension of Sn invariant maps from xi lambda to this phi mu. So, recall phi mu is the representation Sn to GL of M lambda, M mu and xi lambda by definition it is the representation of this S lambda, okay, which we introduced before. So, now so we can actually conclude that here is the lemma. This multiplicity is non-zero, then we must have that lambda dominates mu. So, if this home space home Sn xi lambda phi mu is non-zero, so then we get that lambda dominates mu, and moreover if lambda equal to mu, so then we can conclude that the dimension of this home space xi lambda phi lambda is exactly equal to 1. Okay. So, that means as I promised before, so this lemma concludes that you write this M lambda as direct sum of irreducible representations, then you can see that this M lambda is given by S lambda direct sum of some k mu lambda S mu, where mu like dominated by lambda which is smaller than lambda. Okay, this decomposition we always apply, where S lambda appears inside M lambda with multiplicity 1. That is what this lemma says. Okay, let us prove this. So, we just take a non-zero morphism from S lambda to M mu, okay, because this home space is non-zero. Since this home Sn xi lambda phi mu is non-zero, just a pick T from here. So, T is a map from S lambda to M mu. So, now what we can do, we can actually extend this map uniquely to M lambda as follows. So, M lambda you write it as S lambda direct sum S lambda perp. So, you define this T, the extension from this M lambda to M mu, you just take T of V plus V dash to be just T of V, where V comes from S lambda and V dash comes from S lambda perp. Okay, because any element here you can write it as V plus V dash. So, you extend this T uniquely using this. Now, it is not very difficult to see that it is indeed a morphism of representations, because S lambda perp is also Sn invariant. So, I will leave it you to check that this T is indeed Sn invariant map. Now, since it is Sn invariant map and clearly the kernel of this T does not contain S lambda. So, the kernel of T cannot contain this S lambda, because T is non-zero map defined first on S lambda. Now, we have extended that to M lambda. So, the kernel cannot contain S lambda, and that would imply that immediately lambda dominates mu, okay, using our earlier lemma. So, the earlier lemma says whenever S lambda is not contained in kernel T, then lambda indeed dominates mu. So, now assume that lambda is equal to mu. So, if lambda equal to mu, so then we know that T must be scalar multiple of identity. So, on at least S lambda, okay, because we have seen this whenever lambda equal to mu, when you restrict T to S lambda, it must be scalar times identity. So, now using that you can see that the dimension of this home space Sn xi lambda phi mu can be at most 1. Okay. And since mu equal to lambda and S lambda sits inside M lambda, that would imply that this dimension is exactly equal to 1, and that proves that the multiplicity of S lambda in M lambda is exactly equal to 1. So, now let us use this and then prove that this spec representations they form a complete set of inequivalent irreducible representations of Sn. So, let me state this as a theorem. So, the spec representations xi lambda with lambda partition of n, they form a complete set of inequivalent irreducible, of course, finite dimensional representations of Sn. Okay, all that remains is to show that whenever xi lambda isomorphic to xi mu implies lambda equal to mu. So, here is the proof. Assume that xi lambda isomorphic to xi mu. So, then that would imply that the home space of Sn xi lambda xi mu is indeed non-zero. So, now the home space of xi lambda xi mu is obviously embedded inside the home space of xi lambda phi mu. Now, since this is non-zero inside this, that would imply that lambda indeed dominates mu using our earlier lemma. Now, using the symmetric argument, you can also show that mu dominates lambda, and that would imply that lambda equal to mu. Okay. So, this actually indeed says that whenever these two spec representations are isomorphic, then the corresponding partitions they must be equal, and this actually completes the proof of this classification. So, this actually, like these lectures on this representations of symmetric groups, okay, I just only wanted to do this classification of irreducible finite dimensional representations of Sn. And of course, this is not going to stop here, like there are many interesting follow up questions that one can have. For example, like what is the dimension of this S lambda, the spec modules Indeed, this dimension is given using what is called Hooke formula. And then of course, there is this very important question that is still unsolved, that we also want to understand what happens when you take tensor product of two spec modules. And we know using the theory that that if you take tensor product of two spec module, so this is going to be again written as direct sum of other spec modules with some multiplicities. So, let us call it as C gamma lambda mu. So, now one wants actually have explicit combinatorial interpretation of these coefficients, and as far as I know, like there is no closed expression actually known in the literature, and this is indeed a biggest open problem in this symmetric group representation theory. And like this, like one can ask actually many interesting questions, and there is this sure while duality that actually connects the representation theory of symmetric group with the representation theory of capital GL and C. So, like there are many further readings one can do like from here, and then like I hope you all enjoyed this course and then learned some representation theory from this course. And I hope you will actually continue to actually work in representation theory in the future. I will stop here. Yeah.